Naming non-organic acids. In a CP chemistry class at this school, the decision has been made by the department that we're not going to name organic acids in here, okay? Honors classes name organic acids, but you don't have to. But you do have to name non-organic acids, and you have to be able to write the formulas of non-organic acids if you have the name. Now, to do this, there's a couple of things, there's something you need to know up front, okay? First of all, you got to be able to identify an acid, okay? So non-organic acids will have a hydrogen, or H, on the front, yes, of the formula. So if you hear the name such and such acid, you know that the formula will have a hydrogen in the front. Okay? And we'll treat that acid as if that hydrogen is a hydrogen ion with a 1+ charge. Okay? So an acid hydrogen is always treated as if it has a 1+ charge. In fact, it really does. Sometimes there are some acids that behave like covalent compounds sometimes, and so it's not really an ion, but we can just think of it as having a H+ charge every time. Okay? You also have to know how to name ionic compounds first, because the way that we name all acids, regardless of their class, as long as they're non-organic, is to name them first like they're an ionic compound, and then change the name. So all acids, regardless of their class, and then those names, those ionic compound names, all right? All acids are named like ionic compounds, and then those names are changed. Now what they get changed to depends on the class of acid, okay? And this is a class specifically about naming and not about other things, all right? So this is we're going to divide acids into two classes for the purpose of naming and only for that purpose. That makes sense? Okay, so the first class we're going to name them by, the rules we're going to use for them are binary acids. So I've already defined binary for you, but just to remind you, binary means that this compound is made of only two elements. It doesn't mean there are only two atoms, it means there are only two elements. Okay? Well, we already know one of the elements. Okay, so an acid that's binary has to have hydrogen and only one other element. Does that make sense? All right. Then the other class, for the purpose of naming are acids with polyatomic ions. And specifically, since the acid has a hydrogen that's plus charged, what kind of ion does it have to be? Huh? No, this is a cation. The other part of it has to be, no, this is positive. The other part has to be negative, an anion. Okay? So we can call it acids with polyatomic anions. Okay? You've got to have the compound end up, when you finish with the formula of the name, it's got to have a neutral charge overall. Okay? So if the hydrogen's positive, the other part's going to have to be negative. It has to be. No other way to do it. All right. So we're going to start by learning to name binary acids. Or really, we're learning to name binary acids and to write the formulas from the names. Okay? Binary acids. Binary is a really important thing for you to know. Okay? All of you in here are bipedal, meaning you walk on 2 feet. Computers all run, and your cell phones and digital, everything digital runs on binary code. Okay, your computer only knows zeros and ones. That's it. Okay, everything a computer does is based on zeros and ones. Pretty amazing that it only knows zeros and ones and doesn't know all this other stuff. All right, binary acids. We're going to first name it, as we said, as if it is a ionic compound. Okay? So let's pick a really simple acid, a very common acid, really. It's both simple and common. This one. So we're going to name it like an ionic compound first. Small l, H, capital C, little l. Okay? So if I'm going to name this like an ionic compound, we just spent a whole day on that. We learned some about ionic compounds in the previous unit. In fact, naming ionic compounds that are binary we learned in Unit 3. Well, we're not going to name it like an acid yet. We're going to name it like an ionic compound first. So what would we call this? Hydrogen chloride. Okay? So once we have it into the form of an ionic compound name, now we're ready to convert that to an acid name. And there are 2 or 3 steps. We're going to drop the gin. Okay? High school students shouldn't have anything to do with gin anyway, should they? Okay? That's actually spelled G-I-N. G-E-N means genies. Okay? Gin. Gin means genies. The collection of all genies is the gin. Never mind. Let's move on. We're going to drop the gin.
So we're changing it to what kind of name?
An acid name. Okay? We're going to change IDE to IC. And we're going to put the word acid behind it. Okay? Alright, so we've got hydrogen chloride here. We're going to drop the gin part. Hydro. We're going to keep the ClOR. And we're going to change ID to IC. Yes. And add the word acid to the end of it. Hydrochloric acid. Yep. Well, citric acid is far more complex than this.
Does it have a hydrogen or a hydrogen?
Actually, citric acid has 3 of them. Acid's got more than that, but only 3 of them are the acid hydrogens. Yeah, we'll get to that in the acid unit. This is the nomenclature unit. Okay, we have a whole unit on acids and bases. All right? So that's how you name it. And suppose we want to write the formula from the name. Well, we just undo this. Okay? So if you're given an acid name, and it has hydro in the front, it's binary. change the ic back to ide. Find the element with an ide ending, meaning that it didn't originally have an ide ending, it had originally had something else, and we changed it to ide when we named it like an ionic compound, and put the number of hydrogens we need on the front.
This is writing the formula?
Yep. Okay, so if you have an acid with hydro in the front, the signal right away is that's a binary acid. We know hydrogen goes in the front, so all we have to do is find the back part. It came from ide. We knew how to do that in the last unit. We learned about naming things with an ide ending. We just find the element for which we changed the ending of the name to IDE. And we know if it's going to be an IDE, it's got to be negative, which means it came from the upper right-hand corner of the periodic table. It's easy to find. We narrow down our search. That makes sense? So if I were given hydrochloric acid, I know it's binary because I got hydro on the front. Chloric was chloride. I'm looking for an element that's negatively charged that has ClOR in the front. And the only element that fits that is going to be something up here in this end of the periodic table, like chlorine, which became chloride, which became chloric. Okay? Yes? Got a question? Somebody? No? I thought somebody called my name. All right. Yes? Water's kind of the exception. And here's why I say kind of. While yes. What? Formula for water? Oh, yeah. Hydrochloric becomes HCl. We're just undoing what we did before. So while water does have hydrogen in the front, we, at this point in time, generally say, well, this is kind of an exception. The reality is that water is an acid sometimes. Okay? It's also a base sometimes. But let's save all that for the unit on acids and bases, okay? All right? We'll get to the Bronsted-Lowry theory of acids and bases and figure all that out, okay? So we're going to name some acids from the formula. You can work with a neighbor if you want to, if you'll do so in a low tone voice, a whisper sort of voice. That's the friendly acid right there. So we're going to name those and we're going to write formulas for this is 5, isn't it?
What is the first thing?
Hydrofluoric. Okay?
What's the third one?
All right, so now we're going to learn to name acids that have polyatomic ions. That's the other class of acid that we were going to deal with. Let's see. And before we go there, just to put it on the video, those are the correct answers to the last set. Okay? H2S is hydrosulfuric acid. HBr, hydrobromic acid. HI, the friendly acid, is hydroiodic. H2SE, hydroselenic. Hydrofluoric acid is HF. This is really an insidiously strange, dangerous acid here. Well, it's highly poisonous, and there's not much in the way of an antidote. If you get it on your skin, because of the nature of the anion here, not the acid itself, but the anion part, it tends to burn your skin and you don't even feel it, you know. Theoretically, sneaky. Hydrophosphoric doesn't really exist. I just made this one up, but it's a way of, it's something to figure out.
We should make it.
Hydrochloric, I'm not sure if it exists or not. Right?
Wait, I'm kind of confused. Like, if it's not been discovered yet, then
it's not a matter of being discovered. It means that it just doesn't. It didn't out. It won't do anything with it. It might actually exist, but nobody uses it for anything that I know of. All right, let's move on. Polyatomic ions. All right. Before we go into naming acids with polyatomic ions, let's make sure we're clear on a term that you may have heard me use before. I want to make sure everybody knows what it means. If you look on that list of common ions, on your test references, we're not in an honors chemistry class. You don't have to memorize polyatomic ions. Honors chemistry classes do. Okay? But there are lots of anions, anions being negative ions, that have oxygen on the back. You see that? Lots and lots of them. Okay? Those anions that have an oxygen on the back of the formula have a special name. They're called polyatomic oxyanions. Actually, if you said oxyanion, it would imply polyatomic, because the only way to have oxygen in the back is if something else is in the front, so we don't even need the word polyatomic. Oxyanion is a polyatomic anion, anion being negatively charged ion. An oxyanion is a polyatomic anion that has oxygen on the back of the formula. Well, that's what we think about it. Okay? It's actually a bit more complex than that. We'll try to keep it simple. Okay? So I need somebody to pick for me from that list an oxyanion. Do 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 do. Come on. I want an oxyanion. I just pick one. Iodine. What did you say? Iodine. Okay, here we go. Iodine.
What was an oxyanion?
Oh, it could have been
Any one. That's what, 20-something, 30-something, I don't know, a bunch of them. Iodine. What is the formula for iodine? What is the formula?
IO2 negative.
IO2 negative charge. Okay? Alright. I want to build an acid. I want to build an acid on this polyatomic anion we call an oxyanion. Okay? So if it's an acid, what does it have on the front? Hydrogen. Not hydro. Hydro is actually only used when we have a binary acid. So these are not going to be binary anymore. So what's the charge on our hydrogen if it's an acid? 1 plus. So what I need is H plus and our anion, and I need to figure out what ratio of these gives me a neutral charge. We're balancing a formula. How many of each of those do I need? One of each, because they're already 1 plus and 1 negative. They cancel out automatically. Don't have to do anything else, right? And so this formula is HiO2. Okay? So, what I want to know is, how do you name this thing? And from the name, How do I get a formula? So we're first going to name it like what? An ionic compound. All our acids that are not organic are named first as if they're ionic compounds. So how do I name this like an ionic compound? Hydrogen iodide. Okay? What did I write Na for? I don't know. Oh, that's what I want, yeah. First name like an ionic compound. So hydrogen iodide. Okay? Now, with these kinds of acids, those with polyatomic ions, we are going to, for the most part, drop the hydrogen altogether. Okay? So when we name it, I'm going to name it without the word hydrogen. Not going to shorten it to hydro. Hydrogen's is gone. Okay? Drop that entirely. Anions with ITE endings are changed to OUS. And anions with ATE endings are changed to IC. Not iodic. Ite gets changed to us. Iodite, ITE gets changed to OUS. Oh, I thought you said iodic, I'm sorry. It is iodous acid, yes. Okay? And then we're going to put acid in back. Alright? In the back of it, behind it. Separate word. It's a caboose. Well, sometimes you think of a caboose as being attached, and it's not really attached. Okay, I'm sorry. She liked caboose, we'll call it a caboose. There we go. Alright, so HiO3 is, I'm sorry, O2, thank you, is iodous acid. That makes sense? Alright, so now we're going to practice. Oh, and to undo it, you just undo it. If I have iodous, OUS, or IC endings, that's a polyatomic ion. If it's OUS, I'm going to look for an ITE ending polyatomic anion, an oxyanion, okay? So I want to look for iodite. I just look on the list of common ions until I find iodite. I put as many hydrogen ions on the front as I need. The formula is HiO2. Make sense? Okay? If it has an IC ending, say it was iodate, which I started to write a while ago. If it was iodic acid instead of iodous acid, the IC ending means the polyatomic ion originally had an 8 ending. So I just look for the polyatomic ion iodate. Okay? Make sense? And you put enough hydrogens on there to balance that out. Alright, so we're going to write formulas. Yeah, I think it's cool.
Oh, and then I cried at that movie. I cried at that movie.
You know, I don't mind you guys talking while you're doing the work if it's while you're doing the work. But some people get so excited about what they're talking about, they forget about the work. Sure. If you can't write and chew gum at the same time, don't chew gum. We're not supposed to be chewing gum. You're right. It's just kind of a joke about writing and doing the work. No. No chewing gum in here.
What a revelry.
It's like eating in here. You don't eat in here or drink in here except for water. And then only as long as you follow the rules about the water. It's a safety issue in a chemistry lab. Same thing as eating. You don't know what kind of chemicals have been in the room, therefore you don't know what's been on the desk. And if you open up your chewing gum on your desk and it gets those chemicals from your hands onto your chewing gum, you're chewing on chemicals that can hurt you. Like hydrochloric acid, which is poisonous.
Has a nice sour